Hi, today we're going to start talking about the material in Chapter 3 of your textbook. And Chapter 3 is the part of the text where we start to get into the building blocks for inferential statistics. And remember that that is one of the major overarching branches of statistics. We've already talked about descriptive statistics, which are statistics that we use to describe a set of numbers or a data set that we have in front of us. But inferential statistics are kind of the bread and butter of the rest of this course. Those are the statistics that allow us to take what we know from a group of numbers or from the data that we have from our own research study and draw inferences to the general population that we're interested in. So let's get into it. I'm going to start with z-scores. And before we talk about z-scores explicitly, I'm going to tell you a little story about my weekend. So let's imagine that I went out on Saturday night with a group of my friends. And if you're from Sacramento, this saloon might be familiar to you. We'll say that I went to Shady Lady Saloon. It's down on R Street in Sacramento in Midtown. And I love Irish Stout. I'm from Boston. I'm Boston Irish. I love to drink Irish Stout. It's a little hot for it these days. But say I ordered myself an Irish Stout and it cost me $10. So depending on the context, you might be thinking, wow, that's a lot of money, or that's a really decent price. So there's a lot of questions that we might ask ourselves, right? So knowing one score, just knowing that my Irish Stout cost me $10, or that the value of my Irish Stout was 10, doesn't tell us much about the whole distribution of possible prices. I only know a single score. So without more information, I don't know whether this is a reasonable price or a pretty typical price, or if it's an outrageous price to pay for my beer. And that means it could be outrageously high or outrageously low. We might need some other information to determine the answer to this question. So, for example, we might be interested in the mean. Did I pay more or less than the typical price for this particular Irish Stout? Maybe it's a really rare brand or really rare specific Irish Stout that's only released a couple times a year. So maybe most bars are charging $15 for this particular Irish Stout. In that case, then my $10 Irish Stout would be relatively cheap, right? But if this is just your basic Irish Stout that most bars are selling for $5 or $6, then I probably overpaid for my Irish Stout and it was probably on the higher end. I'd also be interested in knowing the standard deviation of that distribution of prices. I'm interested in knowing how much deviation there exists in the prices of Irish Stouts across other bars. So if the mean is $7, are most bars charging at exactly about $7, or is there a lot of spread in the prices that different bars use for this particular Irish Stout? So we are going to use both those pieces of information, the mean and the standard deviation, to figure out if my Irish Stout was actually priced reasonably. And we're going to do that by calculating what we call a z-score. And a z-score is a score that describes a single score in terms of where it falls relative to other scores in the distribution. Okay. So in other words, this allows us to compare a single score to the mean, taking into consideration the spread of the distribution. So let's work through another example. And this one, in this example, we'll actually go through the calculation. So in this example, we want to know if an individual is a morning person, right, relative to their peers. So we ask a group of individuals how much they would rate themselves as a morning person from 1 to 7, with 1 being, I'm not at all a morning person. I hate waking up in the morning. And with 7 being, oh, I'm extremely a morning person. I love to get up and get going first thing in the morning. So one of our participants, Jerome, reported that he is a 5 on this scale. So he is pretty much a morning person, maybe not all the way gung-ho about it. So in this case, We want to know how Jerome compares to his classmates, but we don't have any individual scores. So if we don't know how his classmates reported, then how could we know if Jerome's score is if he's more or less of a morning person than his peers? Well, if we do know that the mean score for his class is 3.4 on this scale, and the standard deviation is 1.47, or in other words, on average, people rated themselves a 3.4 on this scale, give or take 1.47 scale points. Now that gives us something to work with. Now we can, right off the bat, say that Jerome is more of a morning person than the average individual in his class. If the average individual said they were 3.4 on this scale and Jerome said that he was a 5, then we can say that Jerome is more of a morning person than his class on average. Also, if we know that the standard deviation is 1.47, then we know that people who are one standard deviation away from the mean or one standard deviation above the mean would have a morning personness score of 4.87, and Jerome's score is 5, so it's just a little bit above 4.87. So in other words, Jerome's score on this scale is between 1 and 2 standard deviations above the mean. Okay. And just to be thorough, note that 1 standard deviation below the mean would be 1.93, and 2 standard deviations below the mean would be 0.46. Okay. So now that we have this information, we can talk a little bit more fluidly about how Jerome compares to the other individuals in his class when it comes to how much of a morning person he is. So Jerome's score of 5 is above average, and he's more than 1 standard deviation above average. So what we'll do is we'll use this information to convert Jerome's score into a score that will give us this information in a more straightforward way. So the way that we'll do that is to use this formula you see on the screen. This is the formula for a z-score, and z-scores are really crucial to statistics. The z-score formula is one that you'll see over and over again if you haven't taken a statistics class before. This might be the first time you're seeing it, but you'll get used to it. And for others of you who've taken statistics before, you probably already know this by heart. The z-score formula is in the numerator just a deviation score. Recall that terminology. A deviation score is an individual's score, x, after you subtract out the mean. So in other words, that's the deviation score represents how far your own score is from the mean score of the sample. So that's here, x minus m. And then in the denominator of the z-score formula, we divide by the standard deviation of the scores. So if we do know that the mean of the sample on morning personness is 3.4 and the standard deviation is 1.47, and we know that Jerome's score is 5, then we can just plug in all of those pieces, right? We know that Jerome's score, x, is equal to 5. I know that the mean for the sample across all the participants is 3.4, and I know that the standard deviation across all the participants was 1.47. So I didn't even need to know the individual scores of all the people in the classroom. As long as I know the mean and standard deviation, then I can calculate a z-score for Jerome. And if you go ahead and plug those values in, you get Jerome's z-score is equal to 1.09. Notice that we could also work backwards. I could flip that formula around and figure out Jerome's raw score if I already knew Jerome's z-score. Okay, so let's interpret this. What does a z-score of 1.09 mean? A z-score of 1.09 is a score that's in units of standard deviations. So you already noticed that Jerome's score of 5, right? Jerome's score equals 5. we knew that his score was a little bit more than 1 standard deviation above the mean. So that's exactly what the z-score will tell us. It tells us that Jerome's score is exactly 1.09 standard deviations above the mean. Notice if this z-score was negative, it would tell us that Jerome was 1.09 standard deviations below the mean. So positive z-scores are scores that fall above the mean, and negative z-scores are scores that fall below the mean. So importantly, z-scores are in units of standard deviations. We often call z-scores standardized scores, and that's because when we calculate z-scores, we're taking a raw score in whatever units it originally existed in, and we're transforming it into a z-score that's in units of standard deviations. And because all z-scores are in units of standard deviations, we can compare apples to oranges, right? So if apples exist on the apple scale and oranges exist on the orange scale, but we transform those both to standard deviation scale, then we can directly compare them. Z-scores, by definition, fall along a normal distribution. So all z-scores, if we created z-scores for every individual in our sample and then plotted a histogram of those scores, it would look exactly like a normal distribution. So remember that a normal distribution is symmetrical, unimodal, and it has a peak in the center. A lot of distributions are approximately normal in nature. And I have a question for you here. It says, why? Let's think about this. It's because most of the values fall around the mean. So we could think about it this way. Irish Stout will cost about the same in most bars, give or take $1, right? However, some bars will charge way too much and some bars will charge way too little. So there's fewer bars that are charging extreme prices for their beer, whether they're extremely low or extremely high. So that's why the height of the curve is low in these tails. Because remember, this curve reflects a histogram. The peak of the curve is in the middle of the distribution or at about the average cost, because most bars are going to be charging about some average price for the beer. Okay. Now here are some more qualities about a normal distribution. A normal distribution will always have a mean equal to 0. This is the standard normal distribution. So the standard normal distribution will always have a mean equal to 0 and a standard deviation equal to 1. Excuse me. Also importantly, 100% of the z-scores fall below this curve. So again, if we had computed a z-score for every individual of our sample, then all of those z-scores go into this distribution and make a perfect normal curve together with all the scores combined. Positive z-scores, as I've mentioned, are scores that fall above the mean, and negative z-scores are scores that fall below the mean. And because this is a totally symmetric distribution and has a mean of 0, then we know that 50% of the scores will be negative, and in other words, will be lower than average, and 50% of scores will be higher than average. And again, remember that's once we convert everything to z-scores. So because the normal curve is so consistent, we can actually figure out exactly what proportion of scores fall within different regions of the curve. And this will be really helpful to us. So we can calculate the precise percent of scores that fall between the mean, or a z-score of 0, and 1 standard deviation above the mean, for example. And in fact, we know that 34% of the scores will fall in that region. So that's between the mean and 1 standard deviation above the mean. Always, in every single normal distribution, 34% of z-scores will be between 0 and +1. This will be really useful to us. These different proportions or percents that you see on this diagram, these are called the empirical rule. The empirical rule tells us exactly what proportion of scores fall within different regions of this curve. So notice that 2% of scores, only 2% of scores, will be above 2 standard deviations above the mean, or will be higher than 2 standard deviations above the mean. That means that it's really unusual to have a z-score that is more than +2, right? Z-scores that are between positive and -1, or in other words, scores that fall between 1 standard deviation below the mean and 1 standard deviation above the mean, are very likely. In fact, 68% likely. Okay, and we can calculate the percentage of scores that fall above or below the mean or between 2 different values very specifically using what we call a z-table. So if you have a particular score here, this is someone's z-score, then we could actually look up that z-score in what we call a z-table, and there's a z-table in the back of your textbook, or you could look it up online. If you look up that z-score in a z-table, it will tell you exactly how many scores are lower than that z-score. Or in this case, I might want to know how many scores fall above this particular z-score. And a z-table will tell me that information. And remember, that's only possible because we've converted our scores into z-scores, which fall along a perfect standard normal distribution, which we know how to work with. So if we did want to work through an example using the z-table, let's just pick a value. Let's say I calculated a z-score for someone in my sample, and their z-score is positive 0.52, right? So I plugged my person's score into the z-score formula, and I got 0.52. Okay, what does that tell me? Well, I know that it tells me that this individual scored 0.52 standard deviations above average. So about half of a standard deviation above average for the sample. Because remember, z-scores are in units of standard deviations. So this person scored half of a standard deviation above average. Okay. Well, how many people scored above that value? I can look right here. I look up my z-value in the z column. I find my z-value of 0.52. And if I want to know how many people fall above that person's score, then I look at the percent entail, right? Because my score is over here. I say this is 0.52. I want to know how many scores fell above that score. Then I could quickly glance and see that 30.15% of people had a score above this individual, or had a score that's higher than this person. These are some really helpful rules to figure out how to read that z-table. So notice that the z-table gives you a few columns. There's the z column, that's where you have to look up your particular z-score. But then it will tell you either the percent of scores that fall from your z-score to the tail, that's the one we just looked at, or it tells you the percent of scores that fall between your score and the mean. So in some cases, we may need to take advantage of the fact that we know 50% of scores fall on half of the distribution. So if my z-score is positive, for example, in this first row, that's where I'm looking. If my z-score is positive, and I want to know how many scores fall above this individual z-score, then notice I'm looking at percent in tail. A drawing will also help you here. It will always be useful. So in this case, my z-score is positive, so it's above 0, and I want to know how many scores are even higher than that, so I look at percent in tail. If my z-score is positive, so it falls on the right-hand side of the mean, but I want to know how many scores are lower than my score. That means I want to know how many scores are to the left of it. In this case, I need to know how many scores are in this shaded region. All the table will tell me is this piece. The table will tell me that a certain proportion of scores exist from my z-score to the mean. And then I need to know to add 50% to that value, because I know that 50% of values are in the rest of that shaded region. Okay. And you can look through the next 2 rows to try to get a sense of the information there, and let me know if you have any questions. Okay, so let's do an example together. We have some step-by-step instructions for figuring out the percent area above or below a raw score or a z-score. So if we're given a raw score of 125 on an IQ test, and I want to know how many people or how many scores are higher than this score of 125. Well, if the raw score is 125, then I know the first thing I need to do is calculate a z-score. So I use this formula here. So I have x is equal to 125. I have some information for you here. The mean is equal to 100, and the standard deviation is equal to 15. So this is typical for an IQ test. So once I plug those values into my z-score formula, I know that Sharon's z-score is 1.67. So I drew out my normal distribution here, and I mark Sharon's z-score. Z equals 1.67. Okay. You'll get used to drawing that normal curve. After you calculate your z-score and you draw your normal distribution, we could make a rough estimate using the empirical rule of how many scores fall above my z-value. So if I know that Sharon's score falls somewhere here, right? So about 34, and then maybe another 10%, maybe about 44 exist over here in this region, maybe about 44. So I don't know, maybe a little bit more than 2% of the scores are higher than Sharon's. Well, we could figure out the exact percent now using the z-table. So I open up my z-table, I look in the z column to find 1.67, the z-score I calculated for Sharon. And what column will I look in? Well, because we have a score that's on the right side of the distribution, and I want to know how many scores are even higher than it, then I'm interested in this shaded area here, right? And in that shaded area, to get that shaded area, the proportion of scores in that area, I will look up the percent in tail. And I can see that 4.75% of the scores fall in that shaded area. Or in other words, only 4.75 people have an IQ score that is higher than Sharon's. And notice that if I were interested in the number of individuals who had a score below Sharon, then I would have to look up mean to z and then add 50%. Okay, that's the end of this lecture, and notice that there's one more lecture for chapter 3.